Hi, I'm Kostya Osipov. I live in Moscow, and this talk is about avoiding data hotspots at scale. So this is a P99 conference. It's about latency, not scalability. And let me begin by explaining why I think this talk is worth your time. In the past, we used to attribute latency, especially tail latency, to I/O bottlenecks, I/O queuing of the operating system, and this impact of non-universal I/O performance was non-negligible. We are in 2020s, and NVMe devices are a commodity. Modern programming techniques include such frameworks like Node.js, Tokyo, C-Star, which use reactive programming, asynchronous I/O. And in short, you can put the blame on the tail for the tail latency on your database or your system software anymore. So what is the number two reason for high latency? I believe it's hotspots. So better hardware, software, but in a new mobile-driven and data-driven world. So every decision is data-driven. Most of our interaction with the world is using a laptop or mobile phone. So enterprises have dozens and dozens of existing data system, data silos, and they require new ones to serve new use cases. And all of these new data systems, databases, event queues, and so on, they sort of look at the same data, but in a different way. And also they, of course, collect much more data, like data from devices, from IoT, and so on. And as enterprise architects adopt new systems, like we get sort of a zoo of systems in an enterprise landscape. It's like a high diversity and even growing diversity. Perhaps you're aware of a RAM conjecture, RUM. It states that we cannot design a storage system that is optimal for all of the three things at once, like reads, perform fast reads, efficient reads, updates. And updates includes maintaining freshness of data and also be optimal in memory usage. So this room triangle, it has lots of points. You can do multiple trade-offs, different trade-offs, but horizontally scaled systems, they use only a few patterns. So in this talk, I will focus on these sharding patterns, scalability patterns, and see how they can lead to hotspots. There are many things related to sharding. It includes like rebalancing, storing metadata, routing queries to data. Here, I'm only going to focus on how we slice the data. So we are not, just for simplicity, we are not going to cover the other topics. Besides, commonly, as I mentioned, we duplicate our data. So we store it in, say, OLAP system, OLTP system. And we can store it even in an OLTP system, we can store it twice using indexing, materialized views, and so on. So I will not cover this in this talk, but you should keep in mind that hotspots often occur in the secondary dimensions, like in a materialized view or on a secondary index and so on. So let's begin with some basics and look at how we can actually partition our data across multiple servers. And the most common way to do it is a hash-based partitioning. So partitioning, generally sharding, is just it's a way to map data to a specific server. It's a mapping. You could view it as a function or a table. And hash-based partitioning is applying a hash function to the key. Usually it's a primary key, but if it's a secondary index, it can be a secondary key. And some other systems can use multiple keys to calculate the hash. And then the hashed result is used to determine where to store the data. There are multiple hashing algorithms that are common. Most common one is consistent hashing. In consistent hashing, servers and keys are put on a so-called consistent hash ring. It's essentially a range of a numeric range, and it just connected. 0 is connected with the end of the range, and we every server is responsible for its own part of this range. So when you add a new server, it also is put somewhere on the ring and takes ownership of the data that's between its position on the ring and the next server on the ring. Another technique is Kitama. Kitama hashing, it is more math based, and nowadays it's less frequently used. There is also rendezvous hashes and so on. The reason hash-based sharding is so popular is that it is not only an efficient way to scale capacity, it provides some kind of randomness. Not every event is not every data stream is sufficiently random just by design. There are monotonic sequences like timestamps, there are auto-increment sequences, and passing them through a hash function allows to map all of these monotonic sequences to pretty much random node in the cluster. However, you should keep in mind that randomness is not the same as fairness. If you go to a casino, say, and spin the wheel 100 times, you're not guaranteed to get all of the distinct numbers. You are not even guaranteed. Most likely, you're gonna have more blacks than you have reds, and so on. So this is by definition non-uniform. So different vendors approach this problem differently. Some vendors, like Cassandra and Scylla, allow to change data location only when you add or remove a node. Other vendors like Couchbase or Mongo can split an existing range into smaller ranges when it grows too big. This is an illustration from Couchbase manual that highlights that Couchbase uses buckets. A bucket has a fixed size, and when the bucket grows too big, it's split into multiple buckets. MongoDB uses the similar technique, and when its bucket of 64 megabytes is overflown, it's split, and the location of every bucket is independent. But even a perfectly distributed set of buckets is still prone to hotspots. There are 3 reasons for this. An individual key can be too big, or an item associated with it, and it's impossible to split. For example, Cassandra recommends that each partition is only less than 100 megabytes. But we've seen partitions in Scylla that are 10 gigabytes or even 100 gigabyte partition, and this is just how data is distributed in a real-world scenario. There is nothing you can do about it. The second reason, it's even if data is uniformly split according to capacity, some partition can be more frequently used than others. Like that's different data temperature. And you can't really balance both. Either you have some hot partitions, or you have some underutilized partitions. And if a single key is very frequently used, there isn't much you can do about it. And the third reason, and it's on the right on the slide, is some of the queries that you do, they don't map to a single partition, to a single key. By definition, they need to scan the entire range. For example, you store data according to, say, a user ID, but you need to retrieve it according to a timestamp. So that's the common case for MapReduce queries. Range-based sharding is designed to alleviate the past limit. Like you can efficiently execute range queries if you use range-based sharding. The idea of range-based sharding is that the mapping between the keys and the nodes is a table that stores key ranges. And for example, in this picture, you can see that there is a range of keys between min key and -75, -75 and 25, and so on. Similarly to buckets, key range can be split if it grows too big, if it contains too many keys. But unfortunately, range-based sharding presents its own kind of hotspots. When, say, your new keys are monotonic, you like any kind of monotonic data, for example, IoT sensor data can be pretty monotonic. It can generate a record every second. New keys tend to end up at a very specific range, and even if it grows big, it is split. The new keys again are at the very end of the partition range. Many systems which support range-based sharding acknowledge this limitation. So, for example, Cockroach DB, which does provide a range-based sharding because it claims that range-based sharding is more efficient for SQL systems, also provides a hash-based sharding as an option. And this is a piece of a MongoDB manual where the vendor acknowledges that there is no universal way to shard. You have to choose whether you want to avoid one kind of hotspots, that is, hotspots related to MapReduce and range queries, or the other kind of hotspots when inserting monotonic data. The same quote is from a spanner manual here. So what are the techniques to avoid hotspots? I'll begin with those that can be applicable to range-based sharding. So one of these techniques is called bit reversing. When you generate a unique primary keys that are numerical, the higher order bits can be distributed evenly over the entire number space by bit reversing the number. So like in this illustration, I'm using a timestamp, but I bit reverse the timestamp. So every second pretty much ends up on its own partition. This technique is, of course, applicable for a primary key, but has no practical application for, say, secondary keys or materialized views, because you can't, the whole purpose of creating this is that you get the data in a certain order. So beware that even if you solve the problem of hotspots for the primary key, you can still get code when you create materialized views on secondary keys. Another technique is building compound keys. This also helps you avoid very large partitions. If you use a non-monotonic field as the first component, this improves randomness, and you can use a monotonic field as a second component. And if you don't have too much, so that allows every, say, a user ID and a day event, or user ID and a post ID. This pair ends up independently on its own partition. Or you can, if you want to make sure that actually the second type ordering is the second key, all of the values of the second dimension, second key end up on the same partition, you can use what Scylla and Cassandra call clustering key. This makes sure that every partition is the data is distributed according to the first component, but is ordered according to the same component, to the second component. This is why these systems are sometimes called key value systems. So there are two keys according to which you order your data. And there is a special trick to speed up queries that retrieve the most recent data from this kind of distribution. Imagine you have, like in this example, a user access log, which stores user ID and events related to last access, so a timestamp, and you want to retrieve the most recent accesses from your partition. By sorting this last access column in descending order, you make sure that the most recent events are closer to the beginning of the partition, and this retrieval is efficient. Another technique to reduce hotspots and reduce MapReduce queries is used by systems that support joins. This is an example from VaultDB, which is a transactional SQL database that supports horizontal scaling, and it suggests its clients to replicate dimension tables in a star schema. So if you know what star schema is, you have fairly small dimensions like product names, customer names, region names in this example, and fairly big fact tables where you store, say, orders or sales or shippings or whatever you generate on a daily basis. So if you replicate your dimension tables on every shard, you make sure that joining with them is going to be efficient. And this is a quote from a VolDB technical paper from 2015. So I'm not going to talk a lot about good and bad shard keys here, but I want to say this. If you design, say, a data warehouse, you can use a Kimball or Data Vault or some other kind of modeling, and your modeling technique helps you create a system that's both maintainable and efficient. If you say use domain-driven design by Eric Evans to design OLTP system, you still have to think about avoiding hotspots, avoiding big partitions. So it's like a secondary dimension. And unfortunately, you cannot abstract yourself away from the actual implementation. You have to keep in mind that you have to make sure that your partitions are fairly small, not too big, not too small, yet they include the entire relevant domain so that all of the relevant data ends on the same shard and so on. There are some special cases for hotspots which can be applied if some of the constraints that OLTP systems need to satisfy are not present. For example, messaging systems which do not require a strict FIFO order, they can use two dimensions for sharding. One dimension would be a timestamp, of course, and another dimension could be some property of the event that's being queued. So, for example, Kafka does not guarantee a strict FIFO order within a given topic, but only within a given topic for the events with the same sharding property, sharding attribute. And this is, in many cases, this is okay. So this allows systems to scale, and not so strict FIFO is acceptable. You can also not use a sharding key, and in that case, you do get a strict FIFO order. This also works very well with expandable data. So if imagine you only want to store events for a week or a few hours, and by storing events in a single, say, a single broker is a single server, and every server uses objects called segments to append events to new events to. And by storing them in timestamp order, data can be expired by removing entire segments, not removing individual records. So this is another application of this special requirement, a special sort of restriction that you don't have to provide everything like in transactional and serializable way. Scylla implements continuous data capture, and it uses some of the similar techniques to shard, to collocate CDC streams with the sources of CDC streams. Finally, there is a huge domain of sharding in a data warehouse. And data warehouses are also special cases because they don't have OLTP constraints for mainly deletion and updates of the data. They are not required to be as performant for deletes and updates as OLTP systems. So they can pre-order data and store it in multiple different ways. They are sometimes, these sorting orders are sometimes called dimensions, to accommodate different kinds of read queries. And say if you take Vertica, which is an enterprise data warehouse system, it has multiple ways to slice and dice the data. And finally, it calls sharding actually segmentation. So, and you can segment your data in Vertica in multiple different ways at once, and this just creates multiple copies of the same data. Within a given node, the data is further split into partitions, and partitions are further split into chunks, and so on. So if you this from the RAM conjecture point of view, this is a very read optimized scenario. But one important, I would say, observation from the system could be applied to OLTP systems as well. Analytical systems allow you to collocate your different tables according to a certain same dimension. For example, imagine you have customer ID present in multiple tables in your system. You can shard all of your data according to the same sharding key. Currently, not too many systems allow you to supply a sharding function independently for every table. So usually sharding is something built in, and you only select the keys, and after that the system shards the data automatically. And so this could be a useful addition to LTP systems. Let's recap. There is no silver bullet for partitioning your data that would solve all of your scaling challenges, and good recipes for sharding are not innumerable. They're limited, so there is no point to, first of all, the goal of this talk was to look at the different ways to partition data and point out that there is a limited number of these ways, and there is no point in having too many systems in your landscape. You can have only as many systems as you need to have dimensions for sorting your data, and different OLTP, OLAP systems share the same techniques to shard data. And this approach, of course, can be used with the event sourcing, CQRS, and other enterprise scaling patterns that allow you to build data pipelines and combine multiple systems in a single landscape. Thank you. This was a talk about avoiding hotspots at scale. My name is Konstantin Osipov, and here is my Twitter. I work for Scylla, and you can reach me using this email. Thank you.